And with that, I think we're ready to turn over to our honoree, David Rind, who is giving a bonus lecture because this one actually isn't in the book, but we wanted David, of course, to start off the webinar series. So David's going to speak about instability of the North Atlantic circulation in a warming climate. And then, as I said, we have a broad remit and broad set of topics. Then the second lecture today I'm going to give about the impacts of climate change on agriculture, food security, and health. David.
Thank you, Cynthia, for that very flowery introduction.
Well, you know, agriculture, you know, bounty.
As Cynthia mentioned, ironically, the first talk in this series for this book is on a subject that is not in the book. Given that this was nominally a tribute to me, I felt somewhat queasy about contributing to a book, a tribute to myself. However, I have no such qualms about contributing to this webinar. And in this case, I'll be discussing a paper that came out earlier this year about a topic that's also associated with a warming climate. In this case, the instability of the North Atlantic circulation. The North Atlantic circulation, or as it's often called, AMIC, the Atlantic Meridional Overturning Circulation, or as it's also often been called, a conveyor belt, has sinking waters in the North Atlantic, southward flow at depth, upwelling water at high southern latitudes, and then return flow at the surface, transporting both heat and salt. And this return flow, at least part of the Gulf Stream and the North Atlantic Drift, contribute to that return flow. The water sinks in the North Atlantic because it is both cold and salty. Both cold and salt increase the density of the water so that it can sink, the surface water. There has been an increasing suspicion that this circulation may very well be unstable. In fact, earlier this year in April in Nature, there were several different papers and an editorial coming to the conclusion, based on either sediments or sea surface temperature patterns, that the Atlantic circulation is now at its weakest point than it has been over the past 1,000 years. There was another study previous to that that said that since 1850, it may have decreased by about 15%. But in addition to those more recent potential changes, and to be honest, we don't have good measurements of the Atlantic circulation, especially over time. Observations of the ocean are one of the weak components of our observing the climate system. We do have indications that around 1,300 years ago, as the Earth was coming out of the last ice age, in other words, it was slowly warming up, suddenly the circulation in the North Atlantic was reduced to a great extent, plunging the North Atlantic and the surrounding region into near full glacial conditions. That lasted for about 1,200 years. Then suddenly it returned and overshot to more than full strength, with very very great warming in the vicinity, and then gradually settled back into the circulation we see in general today. This was called the Younger Dryas event. So given that that happened in a warming climate, and that it appears as if the circulation may already be decreasing, what is the future of this circulation? And if in fact it were to undergo very strong reductions, this would have a lot of consequences. For marine life in the Atlantic, for example, the coral reefs, this circulation is responsible for providing a lot of oxygen for the ocean. Coastal locations and climate worldwide would presumably be affected. People think of this as another one of the tipping points in the climate system. If you reach the point where the surface waters in the North Atlantic become light enough so the circulation doesn't overturn, that could have very rapid and strong influences on many different people and organisms. And following that, it was the subject of the movie called The Day After Tomorrow, which in a span of about 2 hours involved ice sheets migrating all the way down to New York City. Okay, here are some pictures. In the North Atlantic, the dark purple indicates the sinking water, which moves south into the Southern Ocean, and then through various complicated paths, ultimately ends up returning as the Gulf, at least part of the Gulf Stream and the North Atlantic Drift, with this heat being, to a good extent, responsible for the warmth that you see at high latitudes affecting the climate in Western Europe. In contrast, the hypothesized circulation during the Younger Dryas had still some degree of overturning, much weaker, much more shallow, but the whole circulation system did not seem to involve the high southern latitudes at all and was in general much simpler. So one of the questions is, are we going to be returning from this situation back to this one? On the right, you have a picture from the poster of The Day After Tomorrow, and you can see New York City covered with snowdrifts. On hot days, that might seem like a good thing, but in general, it will not be. Okay, here are the questions we're going to address. Why did the Atlantic meridional circulation shut down at this Paleo time period? Why did it stay off for around 1,000 years and then suddenly return with overshooting? Will it happen as climate warms in the coming years? And if so, what will be the real consequences, as opposed to what was seen in the movie? We will address these questions with the help of the GISS Global Climate Model E, and I provide the reference for that model. Now, what we'll do with this model is we will have a number of different simulations and a number of different model configurations and try to use the evidence that the model provides to understand whether the circulation in the Atlantic is that sensitive, and if so, how does this whole process occur? These are the experiment names, and don't worry if you don't remember all these, we'll just sort of go over them as they arise. But there's a pre-industrial control run with 1850 conditions. There are several experiments in which the carbon dioxide is abruptly increased by a factor of 4. In comparison, you may know that the CO2 has risen from about 270 ppm in pre-industrial times to close to a little bit above 400 ppm now. So a factor of 4 increase is very large relative to what happened. And often when uses models in this mode, you give it a very strong impact to try to illuminate the processes that will go on, that maybe you'll see in a more modified form with reduced forcing. In that regard, there's a 1% CO2 increase, CO2 increasing at 1% per year, until we get up to 4 times CO2, it's 140 years. And actually, if you look back over the record, it has been increasing pretty much at 1% per year. So this is not an extreme simulation by any means. Historical simulation in which changes in climate forcing, as best we know them from 1850 to 2005, are used to force the model. And then a series of RCP simulations, which are theoretical simulations of forcings that reach 3, 4.5, 6, and 8.5 watts per meter squared, respectively, in the year 2100. To put that in perspective, doubled CO2 is about a 4 watt per meter squared increase. So these various simulations are going to give us clues as to what the model says and how we can understand them. And one further aspect of that is that we will use 3 different configurations of the GISS model. A non-interactive simulation, in which the forcings are as pretty much as people have observed, but is a simpler simulation. So-called TCADI, in which the model calculates the chemicals in the atmosphere, like ozone and various other trace gases, the aerosols in the atmosphere, which are little particles in the atmosphere, and their direct effects, most direct effects of aerosols are to reflect solar radiation out to space as cooling implements, but there's a little bit of warming in that they can absorb radiation from the Earth's surface as well. And finally, the last configuration is similar to that second one, but it also includes the indirect effects of aerosols. In this case, the ability of aerosols to act as cloud condensation nuclei and therefore increase the optical depth of clouds. And we'll see very shortly that these three different configurations have very different responses in the model. Okay, so here's what happened in these simulations. The top panel shows the results for the 4 times CO2, abrupt 4 times CO2 simulations in the TCADI configuration. The picture shows the North Atlantic overturning magnitude in terms of spurdrips, and the horizontal axis are the experimental years in terms of time. The value right at the beginning for the circulation, the pre-industrial value, is close to 24 spurdrips. Almost immediately, within 50 to 100 years, when the CO2 is increased abruptly by a factor of 4, the circulation drops by 50%. Then it seems to either recover slightly or stay pretty much level for the next couple hundred years, and then it has a subsequent decline down to values close to 0. It stays that way for about 1,000 years, and then it comes roaring back. These are 2 different simulations. And in both cases, you sort of got the same general pattern, but the time scale of return is slightly different. This all happened in the TCADI configuration, which includes the indirect effect of aerosols. Similarly, in the 1% CO2 TCADI run, a drop, a more gradual one, because CO2 is increasing more gradually by a factor of 2, a steady time period, and then a second subsequent drop, again lasting for some period of time before again overshooting and returning to its end value. And notice, by the way, the end value is pretty much like the beginning value, except it went through a very strange trajectory. Let's compare that with the simulations that did not involve the aerosol indirect effect. Both of them, in the abrupt CO2 4 times increase and the 1% CO2 increase, both of them dropped immediately by a factor of 2 as well. But they never had that subsequent drop. They slowly recovered, and they too ended up at value close to the current. So what was it about the TCADI run that gave you something that looked a whole lot like the Younger Dryas time period? Finally, the RCP simulations, as you can see, there's increased greenhouse forcing going from RCP 30 to RCP 85. And what it shows is that the circulation decreases sequentially as greenhouse gas warming increases. This is consistent with the idea that people are suspicious that a warming climate might sort of be an anathema to the North Atlantic circulation. The highest value, RCP 85, dropped and never actually recovered a stable mode. Dropped to near 0 and oscillated, tried to get back, but didn't make it. A thing to keep in mind is that the secondary circulation decrease happened about 250 to 300 years into the run, whereas the first one happened around 50 years. So let's talk a little bit about why these things happened. The shutdown in the TCADI runs occurred when the warming reached about 4 degrees centigrade. This is the global temperature change as a function of time. The TCADI runs are these colors, these 3 colors, and you can see by 250 or 300 years, the temperatures started out in pre-industrial times about 14.5. At that time period, it got up to about 18.5. So a 4 degrees C warming seemed to be a necessary condition for the circulation to suffer its final decrease. However, the other runs, the TCADI run and the NINT run, their warming was pretty similar, maybe slightly less, but not very much less. So that implied that the 4 degree warming was a necessary condition, but not sufficient. The RCP 85 run also got up to 4-degree warming. In fact, it got up to, this is like a 7-degree warming. So it certainly had enough warming to reduce the circulation to 0. But it turns out that with this magnitude of warming, the circulation never could recover stably. Something else to keep in mind. With respect to what actually happened to the global temperatures, in the northern hemisphere, when the circulation decreased, this red line from TCATI, the global mean temperature dropped 1 degree centigrade. Clearly, in the movie The Day After Tomorrow, it dropped a whole lot more than that. 1 degree centigrade drop would not bring ice sheets to New York, obviously. It's not nothing, but it is not a tremendous change. And part of the reason for that is 4 times CO2 is an awful lot of greenhouse gas warming. And that was continuing to warm the planet. In fact, you can see during the time period when the North Atlantic circulation was reduced, the planet continued to warm anyway, just slowly. Then when the circulation came back, the planet warmed a lot more. Okay. And here are the RCP runs. And as we suspected that as the climate warmed further, as you got to higher RCP values, the circulation was reduced more and more. One interesting component is that in this case, there's no difference between the TCATI, TCAD, and NINT runs. All suffer pretty much the same decrease. So there was something about the TCATI 4 times CO2 simulations, either the abrupt one or the 1% CO2 run, that differentiated it from these other 2 runs. And that will be a key to explaining how the phenomena works, and maybe even how it worked in the Younger dryas. Okay. In terms of what happened to the surface air temperature, we're going to show a movie of what happens. And this upper right-hand figure shows the anomaly in North Atlantic deep water as a function of time in the experiment years. So initially what you'll see right off the bat is you get a reduction in the North Atlantic deep water almost instantaneously from the abrupt 4 times CO2 increase of about half of its mean value. As time goes on, when you get to about 200 or 300 years, I'm told there's a technical difficulty we're trying to resolve. Okay. By the time you reach years 200 to 300, you'll see a full reduction pretty much in North Atlantic deep water. And then by the time you get to about 1200 years, it will come roaring back. So we'll see what happens to the surface air temperature in the initial time frame, then when the circulation really is reduced, and then when it comes roaring back. Okay, so we've started. You see the anomaly as it goes about halfway. The globe is really warming. This is the scale. These purple numbers are values greater than 8 degrees. But you see in the North Atlantic a weakness in the warming. And in fact, now by the time we've gotten past EY 200, you have a big reduction in North Atlantic deep water. And you actually have cooling in the North Atlantic. It's not greatly affecting New York or the Northeast US, not even greatly affecting. There's a little effect in Western Europe. Primarily, the effect is to cool temperatures over the North Atlantic. Meanwhile, the rest of the globe is continuing to warm. And we're approaching the time when the circulation now starts to come back. And now when it comes back, you get strong warming in the North Atlantic as the heat transport by the ocean has peaked. And now the circulation has gone back to normal. And this is sort of your equilibrium situation. So the major effect on surface air temperature was some degree of cooling over the North Atlantic, but the rest of the world continued to warm. Okay, so what caused the initial circulation decline? And this is in all of the runs, TCATI, TCAD, and NINT. And the answer is simple: increased precipitation. Shown here in the table for the TCATI run is the experiment year. the pre-industrial control, and then the subsequent years up to EY 150, the global mean temperature. And you can see in the first 5 years with an instantaneous 4 times CO2 increase, the temperature jumped up 2.5 degrees. To put that in perspective, since about 1850, the global mean temperature has risen about a degree. So 4 times CO2 is very strong forcing. The Atlantic meridional circulation at first had no response, but as the world continued to warm, it started to decrease, and by the time you reached 150 years, it was down by about a factor of 2. The precipitation increased initially and then continued at a relatively higher value because the warmer climate can hold more moisture in the air, and therefore there's more moisture available for rainfall. Evaporation, on the other hand, decreased somewhat in this time frame, and the precipitation minus evaporation therefore increased from 1.1 up to about 1.45. What that did is it freshened the water in the surface North Atlantic. At the same time, the water was actually warming. Both factors act to reduce the density of surface water, making the water too light to overturn the same way it had previously. A lot of precipitation in the North Atlantic comes from local evaporation. So why is it that the precipitation increased at the same time that the evaporation actually decreased? And the answer is in this last column, which is the northward transport of latent heat or of moisture through 40 degrees north. This value increased and remained high because the rest of the world was continuing to warm and putting a lot of moisture in the air. And that moisture got advected over the North Atlantic. So even though the local evaporation decreased, the precipitation could stay high, a characteristic of a warming climate, regardless of what is happening locally. This effect of increased precipitation, immediate warming, and making the waters fresher and lighter and warmer in the North Atlantic happened in all 3 of the runs. What caused the second decrease in the Atlantic circulation? And the answer was reduced salinity at the surface, which actually also happened in the first decrease, but this is now coming about in a completely different way, as one might imagine, because it happens only in the Tikati run, not in the other runs. This is the surface salinity as a function of time, various time frames. And you see in the year EY 250, before the circulation had suffered its second decrease, it was already slightly negative in the North Atlantic. The salinity had been reduced. The water was lighter. Then during the time the circulation really shut down, it became much less saline. And when the circulation came roaring back, it became much more saline. And we'll see this led to the overshooting we ended up getting in the circulation. So here we have another movie. Again, we show the North Atlantic deepwater anomaly, which will follow the same path as previously. These are the sea surface temperatures that arise as a function of time. They're anomalies. And this is the surface salinity anomaly. Okay, so we're already familiar with what happened with sea surface temperature to the extent that it's similar to surface air temperature. But notice the surface salinity immediately has become negative. And then it becomes a lot more negative as time goes on and the circulation has been strongly reduced. It stays negative for a long period of time while the circulation is low. Notice the cold sea surface temperatures. These, by their very nature, would have tried to get the circulation to turn back on because cold water is more dense, but the reduced surface salinity prevented that from happening. This is a salinity reduction, not a temperature reduction, primarily. So we're now marching on in time. And eventually we will see the circulation start returning. And as it does, the surface salinity now becomes much more positive as the return of the amplification of the Gulf Stream and the North Atlantic deepwater circulation in general could now advect more both heat and salt poleward in the North Atlantic. Okay. What caused the whole thing to return, actually? And the answer is that while the circulation was reduced, the rest of the world was not sleeping. It continued to warm because 4 times CO2 is a lot of potential greenhouse gas forcing. And the warming, as time went on, this is all during the time the circulation was reduced, intensified at other latitudes and slowly spread downward and poleward until in the year 1350, the temperatures got very warm at depth in the North Atlantic. Just as cold water at the surface would increase the density, warm water at depth decreased the density below. And once the density was decreased below, the surface could now once again become heavier than the water in the column underneath it, and then the circulation returned. So whereas the circulation decrease was a salinity issue, the circulation return was a temperature issue. And the last movie we'll show will be a two-dimensional picture. This shows the North Atlantic circulation. Blue indicates a reduced North Atlantic circulation. This is in the northern hemisphere. This is the temperature structure and salinity structure and density structure as a function of time. This is the time marker, and we'll see along here where we are in terms of years. You can also see it in terms of the years at the top here. So we start off and immediately the circulation got reduced by a factor of 2. And we're in this frame, and the density has been reduced at the surface relative to below by the reduced salinity, and also for the initial decrease by the warming near the surface. Now we've gotten to the much stronger decrease, large decrease in the North Atlantic circulation, low surface density relative to below, low surface salinity, and right near the surface, not too much in the way of temperature change, because we saw the temperatures in the North Atlantic were strongly ameliorated. Okay, we're still in the circulation reduction mode. And now we're moving forward again. Again, still low salinity, low density at the surface. But you notice the warming is now spreading downward in the North Atlantic. And when it reached depth, so that the density structure no longer had the lighter density near the surface, the circulation could overturn and eventually came back. Okay, what role did altered heat transports play? In the movie, The Day After Tomorrow, the idea was that the change in the transport of heat poleward in the North Atlantic was what caused New York to be, it ended up covered with snow. And they didn't show what happened to Western Europe, but presumably they would have not been good there either. We can see here that the northward transport of heat by the overturning circulation did get reduced during the time frame the circulation shut down, and the total northward transport of heat did as well. So why didn't it cool so much, as we saw in the surface air temperature movie, over New York or any place else outside the North Atlantic? And the answer again was 4 times CO2 is a lot of warming. And that warming prevented the extreme conditions that probably happened during the Younger Dryas time period. When the circulation returned, the northward transport of heat now suddenly leapt up, and then we got very strong surface warming. So the heat transport didn't have any tremendous effects outside of the North Atlantic, except during the overturning circulation return when it provided more excessive warming. How about the transports of salinity with time? In this case as well, salinity transport was reduced as the circulation was reduced. But now the transport of salinity didn't really seem to vary much at all because the wind-driven gyre circulation picked up the slack. Salinity transports did not play much of a role during the time the circulation was shut down, unlike what some people would have thought, except when the circulation returned, then the salinity transports increased rapidly, and that helped amplify the circulation. Okay, why did the second AMOC reduction occur only in TCADI? The indirect aerosol effect in TCADI. What is the indirect aerosol effect? It allows cloud cover that exists to become optically thicker and reflect more solar radiation out to space, and therefore reduce the solar radiation that reaches the surface. Shown here are the differences between TCADI and TCAD, the run without the indirect effect, and between TCADI and NINT, which also had no indirect effect. In terms of total cloud cover, these are the years prior to the circulation reduction. TCADI had increases both in cloud cover and cloud optical thickness, and the net solar radiation at the top of the atmosphere and at the surface was reduced relative to both runs, and the SSTs cooled. Less solar radiation reaching the surface, cooler conditions. The cooler ocean then led to reduced evaporation. And this occurred for two different reasons. One is when the water is cooler and the air at low levels is cooler, it can hold less moisture. So it's not as easy to evaporate moisture into that air. In addition, the moisture transport from the surface to the atmosphere is a turbulent process. Remember, in the surface air temperature movie, the air over North America was getting really warm. That warm air was advected out over the ocean, and you had a situation in which you had cooler sea surface temperatures below and warmer air above. That is a very stable condition which cuts down turbulent transfers and contributed to the reduction in evaporation. Once you got a strong reduction in evaporation, then what happens to salinity depends upon what happens to precip. Yes, precip was reduced a little bit in these runs, but the reduction was not nearly as strong as the salinity reduction because the precip was still being fed by moisture advection from outside the region. Therefore, E minus P was negative or P minus E positive, meaning you're freshening the ocean, reducing the salinity. This is the sea surface salinity. And that reduction in sea surface salinity, as we saw previously, led to the second reduction in North Atlantic circulation, bringing it to values close to zero. Only in the TCADI run, because only in that run was the cloud cover enhanced and the solar radiation reduction at the surface occurring. How does all this compare with the Younger Dryas? Well, the time frame for the change does appear to be somewhat similar. It was a very rapid initiation. It stayed off for about 1,000 years. Then it came roaring back and overshot until it then oscillated back to its ultimate state. However, unlike the movie The Day After Tomorrow, the temperature response is much less. Here's an estimated temperature change at Greenland from the Greenland ice core. And there's some uncertainty, but it's thought that the temperature during the time of the Younger Dryas, the strong reduction, as the Earth once again was coming out of the glacial age, of somewhere between 4 and 10 degrees centigrade, lasted throughout the time period the circulation was greatly reduced. And then during the overshooting, the temperature rose by like 14 degrees centigrade, a very rapid, strong rise. Contrary to that, in our simulations here, the temperature dropped maybe a degree or stayed near zero while the rest of the world was warming. And then when the overshooting happened, it came back and warmed another 3 degrees. Again, the amelioration of this impact was due to the higher CO2 levels in the atmosphere that weren't there during the time of the Younger Dryas. So here are the conclusions. The AMOC is reduced somewhat in a warming climate as precipitation increases with the higher moisture content in the air. That gave the 50% reduction in the first 50 or 100 years of this very strong 4 times CO2 increase. And it happened in all the models. If the warming was sufficient, 4 degrees C in this model, the AMOC can be greatly reduced. But again, it required more than just that warming. This reduction arises as a local cooling agent, the indirect aerosol effect, caused a reduction in evaporation in the North Atlantic, while precipitation is less affected. Therefore, the salinity was reduced, and with fresher waters in the North Atlantic, the water was now too light to overturn. The circulation ultimately returned when the continued global warming spread to deeper waters in the extratropical North Atlantic, destabilizing the profile by adding fresher water, lighter water at depth. The reinvigorated salinity transports, when the circulation came back on, caused the circulation to overshoot before finally settling down. So in summary, the warming is slowed over the North Atlantic when the AMOC heads towards zero. But the effect on Western Europe and the North Atlantic, at least in this model, is not very strong. And the warming returns strongly over the North Atlantic as the AMOC returns. And that then did exaggerate the warming, especially over Western Europe and the high North Atlantic. The Younger Dryas, in comparison, had a somewhat similar scenario. As we were coming out of the Ice Age, the CO2 actually started increasing from about 200 to 270 parts per million, which was then part and parcel of adding to the warming climate. Some people think it was the major reason the climate continued to warm. There was also local cooling. The aerosol cooling in this model comes primarily from sea salt aerosols. Well, sea salt was around during the Younger Dryas also in the North Atlantic, so it could have acted as cloud condensation nuclei there as well. But in addition, glacial melting during the Younger Dryas poured cold, fresh water into the North Atlantic, which was another obvious cooling agent. And also the fresh water could have helped reduce the salinity even further. But again, as in the experiment, during the Younger Dryas, the planet continued to warm. Presumably the warming once again spread to depth in the higher North Atlantic. The circulation was destabilized, came roaring back, aided by the salinity salt transport. And all of that, the spreading of the warming, was in a similar time frame to what is seen in these runs. And that is also understandable because it does take a while, presumably maybe the same amount in the model and the observations, for that warming to actually spread. Now, the caveats here. This is not guaranteed to happen. For one thing, in the model, it required a 4 degrees centigrade warming. There's no guarantee that a 4 degrees centigrade warming will actually happen. And if it does happen, this may not be one of the biggest problems that society will have. 4 degrees centigrade will be a hard thing for most living organisms to bear. It depends upon the climate sensitivity, which we certainly do not know perfectly, and also mankind's policies and what happens to further trace gas emissions. Furthermore, regardless of the trace gas emissions, we don't know what the real world climate sensitivity is for increasing CO2. So we actually don't know how much CO2 is required to get to the sort of warming that could trigger this effect. In addition, in this model, it took 4 degrees centigrade, but maybe in the real world, it takes a lot less. That's why people are very concerned about looking for trigger points in the North Atlantic, and why there are some recent papers saying it looks like some of it is starting to happen already with only 1 degree centigrade. Finally, in this case, the aerosol indirect effect played a very important role to initiate that cooling in the North Atlantic as the globe warmed. And it's an understatement to say that effect is not well understood, either in an abstract way or in a parameterization way in the model. The actual reference for this paper, in which there are many more details discussed, including what happened in the Southern Hemisphere, is given below. So to conclude, the potential for the North Atlantic circulation to be reduced as climate warms is very real. And if it happens, there will be a number of consequences, and a number of consequences that we don't understand today. So it is very important for us to be observing the North Atlantic. And frankly, we don't do a good job of it. People have pointed out that the ocean observations, especially at depth in the ocean, represent the least observed component of the climate system. So to have ocean observation programs, and there's several that have now started, to be able to continue to fund them and to expand them is of top priority if this potential weakness in the system is to be ascertained. And maybe if we see something starting to happen, it will give us even further incentive to reduce greenhouse gas emissions. Thank you. Sure.
So the way that you can ask a question is either to, if you click on participants, you can raise your hand, or you can type your question into the Zoom group chat. So if you have a question you'd like to ask, go ahead and raise your hand or type it into the chat. We're monitoring that. And while we wait to see if anybody does type out one or raise their hand, I don't see anybody with that right now. We can look at these questions.
To predict the impact under these ever-increasing complications triggered by human-induced actions. So I think that's very germane to the use of the model that you just presented to explore the Atlantic.
Well, Prasad, thank you for the question. And the direct and honest answer is we don't know because it hasn't happened yet. Models are able to, in general, simulate what has happened over the past 100 years. But of course, we know what happened over the past 100 years. And to say that doesn't influence the modelers is not to be completely truthful. We expect that the physics that is in the models is a good approximation for the physics of the real world. But there certainly are potential complications, nonlinearities, interactions amongst the components of the system that may well be beyond our ability to truly understand. And an example of that, perhaps, is that this past summer showed such extreme warming at high latitudes. Normally, climate models have talked about great warming at high latitudes being a winter phenomenon. But here we actually had it occur in summer. To the extent that really is a product of climate warming, that is something that we did not pick up from models. So I would say that models, the phrase that has been used is through a knobbly glass. You're looking at the system through a knobbly glass. You can get impressions of what's likely to happen, but the details and the circumstances and some of the surprises, it's very possible that is beyond certainly our current modeling capability, and it's going to not be easy for us to be able to understand it. In particular, for the North Atlantic circulation, as I mentioned, it depends upon the sensitivity of the model, the particular forcing, in this case, the aerosol indirect effect, and maybe many other aspects of the system that we don't currently have under our thumbs properly.
Dr. Ravi Fernando, we have our first question. Have similar studies been done to monitor the Indian Ocean as that?
As far as I know, no. The Indian Ocean has not been a subject of paleoclimate interest in the same way the Atlantic has. Since the Atlantic was more associated with the various ice sheets bordering it from all sides to a good extent. So what actually happens in the Indian Ocean? That's really a very good question, and maybe somebody listening to this question will spend time. It's also possible somebody has done it and I just don't know about it. Thank you, Claire. I'm sure when I hear your talk, it will be very clear and comprehensive and understandable and enjoyable. There are a number of different radiative forcings, volcanoes, solar variability, but when we're talking about something on this order of magnitude, it is the greenhouse gases. And when you come right down to it, it is the carbon dioxide that's the issue. There have been a number of attempts to look at the carbon budget in the atmosphere. And to some extent, we have an estimate of how much carbon dioxide we've released from the various fossil fuel generators like power plants and transportation. We also have a good estimate of how much carbon dioxide has actually increased in the atmosphere. And it's thought that about half of the carbon dioxide emitted has remained in the atmosphere. So that means the other half has gone into the system. On a very rough scale, it's estimated that about half of that went into the ocean and about half of that went into the biosphere. So there are also estimates that are made of what will happen in the future. As the ocean warms, for example, it can absorb less carbon dioxide. So that 50-50 breakdown of emission to staying in the atmosphere might change somewhat. On the other hand, there are questions of CO2 fertilization of the biosphere, that maybe the biosphere will be able to pull down more carbon dioxide. But I think if you were a betting person, you might suspect that for at least quite some time, 1/2 of the carbon dioxide that's emitted is probably going to end up in the atmosphere. And carbon dioxide has a very long time scale in the atmosphere, several hundred years. So once we put it in the atmosphere, it isn't going away in a few decades. You're most welcome.